simple graph. N upon 2. In fact, n minus 1 upon 2 will also do. How does one see this? Start with a vertex. If this vertex is adjacent to all the vertices, then there is nothing to prove. Then the graph is connected, of course. So you should have a vertex which is not adjacent to this. This is the neighborhood of that vertex x. Size. So take a vertex y which is not in the neighborhood, y not equal to x. Then y will have its own neighborhood. Why is that? Because the minimum degree is at least n minus 1 over 2. So if you add these up, then you get the number n minus 1 plus x plus y also. That makes a total of n plus 1 vertices, which is contradiction. Or by inclusion exclusion, now follows that there must be something in common. There must be at least one vertex in common. That just says that x and y are connected. This is true for any y, not in the neighborhood. In fact, one can strengthen this further. You see what does this say? If that is given to you, then the diameter of G is no more than 2. Any vertex is at distance 2, at most 2 from x. Not more than that. So I can actually strengthen that theorem. Not only that the graph is connected, but the diameter of that graph is at most 2, is what that proof is saying. Okay. So this is a sufficient condition. This is actually a sufficient condition for graph to be connected. For simple graph to be connected, if the degrees are high, if the degrees are large enough, then the graph is connected. Is it also necessary? Whenever there is a question of sufficiency, a related question is that of necessity and sufficient. So these go hand in hand. Is this condition really necessary for the graph to be connected? Not really, not at all. In fact, if you take a cycle, then each vertex has degree only 2, whereas you can have a cycle with 1000 vertices. You don't require degree to be 500 for the graph to be connected. That's not true. In fact, you don't even require the degree to be 2. It's even okay for the degree to be 1. Okay? Of course, the degree should not be equal to 0. You cannot have a vertex of degree 0. Then the graph cannot be connected. That's clear. Graph will not be, that is asking for too much. But in a connected graph, you could have vertices of degree 1. The end vertices of a path have degree 1. So this condition is not necessary. It is only sufficient. Is it sort of the best that one can do? The answer is yes. And What does that mean? You take a graph, disjoint sets of vertices, n upon 2 on this side, n upon 2 on that side. If n is even, then you are just saying that take half the vertices on one side, half the vertices on the other side. Okay? Then the degrees will not satisfy that requirement. It will be just short. Okay? The degree of every vertex will be n upon 2 minus 1. N upon 2 minus 1, because the total, which is n minus 2 upon 2, so slightly less than that number. But you will have 2. Each degree is n minus 2 upon 2. Therefore, that is slightly short of that, and the graph is not connected. So this cannot really be weakened. Okay? You cannot really write a smaller number here and expect the graph to be connected. This I did when n is even. Work it out when n is odd, the same kind of thing. When n is odd, these numbers are different. Have I introduced these functions already? Yes, this is the ceiling this is the floor function and that is the ceiling function. Okay? So if n is odd, this is n minus 1 upon 2 and that is n plus 1 upon 2. Okay? So that is for connectedness. Some more results of this kind. So G has a subgraph H. So I can find a subgraph that has half the vertices, half the edges from that graph. Original graph is not bipartite, but I can find a subgraph of that graph which is bipartite, and with the property that that subgraph takes out at least half the edges that the original graph has. How does one prove this? Essentially only one way, but conceptual level there could be two ways of doing this. Let bipartite subgraphs can always be formed from any graph. That's not difficult at all. Is it clear? How do I get a bipartite graph out of any graph? Divide the vertex set into two parts. Look at all the edges going from x to y that are there in G. All the edges that are inside x, ignore them. Just leave them out. And that forms a bipartite graph. So bipartite this is not an induced subgraph. This is just a subgraph. Subgraph of G such that E of H is the largest. Take a vertex x here. What are the adjacencies of x? Some are adjacencies inside capital X, some are adjacencies in y. That is how that picture is going to look like. If X is adjacent to 4 vertices here and 5 vertices there. What is it that I can do? I can shift X from capital X to capital Y. I can actually shift, I can change that bipartition. This will obtain a new graph, new bipartite graph for me, because in this bipartite graph, these 4 edges are there in edge, but those 5 edges are not there in edge. They are not there because that's the way we have defined it. If I shift that X to Y, I will lose these 4 edges, but I will gain those 5 edges. Is that clear? Therefore, there is a net gain of 1 edge, which is a contradiction because we assume that edge has largest number of edges. Alternatively, that is a contradiction because we assume that edge has largest number of E of edge as large as possible. So that's proof by contradiction. Else, those who don't like proof by contradiction, this is a constructive proof. It's actually constructive proof. Just arbitrarily, first of all, partition the graph, the vertex set of the graph into 2 parts, X and Y, randomly. Let and x1 in G. If R is less than S, then we can form a new bipartition with subgraph H which will have S minus R more edges, which is a contradiction because we assume that H has the largest number of edges. So R is greater than or equal to S. This is true for every X. Thus, degree of X in H, which is equal to R, which is equal to R, X is adjacent to at least half the vertices of the total number of vertices to which it is adjacent to in H. This is true for this holds. I.e. degree so if you sum this up, what you get is 2 times the, summing all the degrees, what you get is 2 times the number of edges. If you sum this up, you get 2 times the number of edges in G Okay. Yeah, so given any graph, there is a sufficiently large bipartite subgraph that it has, which takes away at least half of the edges. Something good to know. Yeah, in fact, there is a construction here. So this gives me, this tells me that does it really construct a maximum sized bipartite subgraph? The answer is no. It does not quite construct. There may be a bipartite subgraph of the original graph which is bigger than this, which has more edges. What is meant by bigger? Something that has more edges. Yeah, the point is, the way I have written this proof is by contradiction. This could have been written differently, you could do that in a constructive manner. What does that mean? As I just said, begin with a bipartition, V disjoint union of x and y. If x is adjacent to more vertices in that part than y, then shift x to the, keep doing this. You will have to repeatedly keep doing this, eventually reaching a situation where you get an edge such that this is satisfied. Eventually this will get satisfied, one by one, because each time you will keep increasing number of edges. Okay? So the degree of every vertex will actually go up. So this will get satisfied. When it does get satisfied, your algorithm will stop. It will actually stop at that stage. It will actually produce a bipartite subgraph that has at least half the edges that G has, than what G has. Question still remains whether I could have added more edges. Okay, and the algorithm doesn't really answer that. So here is an example to show that this algorithm may not really produce the best possible bipartite graph. Okay, so I have to draw this. Okay, with the adjacencies between x1 and x8. Okay, check that each vertex has degree 5. If I missed out something, then 1, 2, 3. Sorry? X7 has degree only 3. X7 is adjacent to X5. X7 is adjacent to X3. X7 is adjacent to X6. X7 is adjacent to X4. You're right. X8 to X6. Yes, X8 to X6. Is that it? Yeah. So each vertex has degree 5. Yeah. Because the degree is 5, the total number of edges is 8 times 5 divided by 2, 20 edges. Okay, if you now form a bipartition with x1, x2, x3, x4, x5, x6, x7, x8. Then you get 12 edges, which is of course more than what that theorem is saying. The theorem is saying that you should have 10 edges, at least. But if you take x1, x2, x7, x8, that has 16 edges. Therefore, if I had started with this partition, that algorithm actually would have stopped. It will stop because it says that as soon as you have more vertices in the other part adjacent to that given vertex, you just stop that algorithm there. Okay? The pedagogical point that one is making here is this produces a subgraph that satisfies that lower bound. It does not produce a maximum subgraph with maximum number of edges. Okay? It does not really produce something that has the largest number of edges. That subgraph could not have been modified really. You couldn't have really shifted x5 there. That will actually worsen the situation. Just check that. I can't really take x1, x2, x3, x4, x5, shift x5 there, then with 5 vertices on that side and 3 on that side, I will actually get less number of edges. Okay? Therefore, this is maximal. It's not maximum. That actually produces as many as 16 edges. Therefore, as an algorithm, it is not very good. That theorem, the proof of the theorem is not very good as an algorithm. These are aspects that one has to look into when one actually wants to find out how large bipartite graph do I get, etc. So I cannot be just happy with that statement. It's okay to know that I can get a bipartite subgraph with at least half the edges. But in particular situations, I may be able to do much better than that. Okay, now is a definition that I want to make. Fixed. Then G is H free if G has no subgraph H prime isomorphic to H. Example. So let's begin with small examples. Or a triangle. K3 is popularly called a triangle. Do we have examples of triangle free graphs? Yes. Peterson graph is triangle free. Peterson graph has no copy of K3 because the girth is 5. Any bipartite graph is triangle free. Any bipartite graph because it has no odd cycles. It has no odd cycles. In fact, for that matter, any bipartite graph is even C5 free or C7 free, etc., etc. What about graphs that are K2 free? Huh? Sorry? Yeah, it's clear. K2 free graphs are uninteresting graphs. Okay, graph that has no edges at all. There is no point in talking about it. K2 free is asking for too much. That is just asking for too much. Graph that has no edges is clearly uninteresting. No interest. What can one do with graph that has no edges at all? Idea here is I have a fixed n, fixed number n, the number of vertices. I want to find out, suppose n is equal to 10. Let's say n is equal to 10. If I take all possible edges on these 10 vertices, then there are lots of triangles, of course. There's no question, many in fact, so it's not triangle free. So now the question is, you sort of build it up. Start with a graph on 10 vertices that has no edges at all. Therefore, it is triangle free. Add one edge, add two edges, add three edges, etc., etc. Eventually, you will reach a situation which will be sort of saturation, where if I add any extra edge, I will have to create a triangle. Is that clear? A bad way of doing this, for example. Just think of this. This is clearly a very bad way of doing it. I'm not saying you do it this way. Suppose I have 7 vertices. If I draw all these edges, I really cannot add any new edge now because it will create a triangle quite clearly. But this was a bad choice. I mean, I shouldn't have really chosen those 6 edges, etc., etc. So the question is that of n is given to me, and I want to find out how large, what is the largest number of edges that I can get that will still avoid having a triangle. And this is called Mantel's theorem. So let's write the statement. N square upon 4, n square upon, yeah. In fact, let's quickly see how to get, I have not proved that theorem, let's quickly see how to get equality there. Suppose n is even, there are only 2 possibilities, either n is even or n is odd. If n is even, let's say n is equal to 2m, then you can put m vertices on one side, m on the other side, make a complete bipartite graph on these. The complete bipartite graph, being bipartite graph, cannot have triangles, there is no question. It cannot have triangles. How many edges will it have? M here and m word, so it will have as many as m square edges, which is exactly same as what you have. N is equal to 2m. If n is odd, then I cannot put them equally. Then I put them about equal, putting m plus 1 in one part, m in the other part. Getting a total number of edges I'll get will be m square plus m. What will be this number then? N square upon 4, which is 2m plus 1 So 4m square plus 4m plus 1 upon 4, and the integer part of that is exactly m square plus m. So that's okay, because you need to look at the integer part. In fact, a better thing, because number of edges is in. So that equality is actually met. You can get equality there. What remains to prove is that you cannot get anything better than this. You cannot really improve. That is the best that you can get. So proof of Mantel's theorem. What is delta G? It's the largest degree that you get in the graph. So there is a vertex whose degree is k. So there is a 3-tier system that we have created. Okay, the vertex itself, neighborhood of that vertex, the remaining vertices. Look at any vertex here in n of x. Which vertices can it be adjacent to other than x? This vertex cannot be adjacent to that vertex because we are assuming that your graph is triangle free. G has no triangles. So this vertex cannot be adjacent to this vertex. It is adjacent to x, so the only other adjacencies it may have are to n bar x. Let the only vertices to any one of these be adjacent to is over here. Therefore, I have already counted these k edges. If I have to count the remaining edges, I can just look at these vertices here. Because any vertex, any edge now other than these k actually will either have this form or it will be going inside that, that's okay. Therefore, it's enough to count the number of edges, counting over all z's running over n bar x. Okay? This shows that every edge that does not have x as endpoint must have Z belonging to some Z. How many vertices do I have here in n bar x? That is not difficult to calculate. Because there are k here, 1 there, so remaining n minus whatever is over here. What are the degrees of each one of these? At most k, no bigger than k. How many vertices are here? N minus 1 minus k. To that I can also add x, which has degree k, and what that means is the number of edges in G cannot be any more than n minus 1 minus k plus 1 into k. Therefore, if you have k fixed among all graphs that have the largest degree equal to k, and that are also triangle free, the maximum number of edges is no bigger than k into n minus k. Thus, for a fixed k, E of G is bounded by k into n minus k. That shows, for example, if I take k equal to 1, then you get at most n minus 1 edges. If you take k equal to 2, you get only 2 times n minus 2 edges. Therefore, I really have to shift k in order to find the maximum of this. One way of solving this is purely a calculus problem now, elementary calculus question. N is fixed here, k is taking values 0, discrete set of values 0, 1, 2, 3 up to n. What is it that will maximize the product? K into n minus k. So it's as good as saying, which way is it working? For a fixed perimeter, yeah, you are given rectangles with fixed perimeter, the area is maximized if you have a square. So if I take k equal to half of that, k equal to n upon 2, that product will get maximized. Alternatively, graph theoretic way of arguing about this is, which is actually quite good. In fact, I will get this equality here. When will I get equality here? Equality will happen here only if each one of these will have degree k. Only then I will get equality. That is, Z has degree k, each one of these must have degree k, and there is no adjacency here because that edge will be double counted. An edge like this will be double counted, whereas it should not be double counted 2 times. Okay? If I want to get equality here, each vertex here should be adjacent to k vertices there, and therefore equality is obtained here only if I have a bipartite graph. I have a bipartite graph in which in one part I have k vertices, in the other part I have remaining n minus k vertices. And then the question boils down to, among all bipartite graphs with k vertices on one side, n minus k on the other side, which bipartite graph has the largest number of edges? That obviously is obtained when you put about equal number of vertices on both sides. Okay? The expression k times n minus k is maximized. Okay, is that clear? Asking for a triangle free is the beginning of this. Mantel's theorem was proved quite a long time back, this is 1907. This also has many proofs. I will indicate one in a short time. This is asking for K3 free. You could ask for graphs that are K4 free. I will allow K3, but I will not allow K4. What is the largest number of edges you can get? And the right model for this, if you want a K4 free, is what is, instead of bipartite graph, what is called a tripartite graph. Okay, so the edges are allowed only between distinct parts. This will allow a formation of K3, but it will not allow formation of K4. That's clear, because to get 4 vertices, I must have adjacent vertices, one vertex from here, one from here, and one from here. This forms a triangle. But to get a 4th vertex adjacent to all of them, it cannot be in any one of these parts, because this vertex and this vertex are not adjacent to each other by definition. Okay? That is the definition of tripartite graph. One can in fact define in general an M-partite graph. An M-partite graph has an M partition. x1, x2 up to xm, such that inside xi you have no edges at all. So an M-partite graph does allow a Km, but it does not allow a Km plus 1. It does not allow Km plus 1. And the question is, if you want to avoid a Km plus 1, what is the largest number of edges you can get? And this is called Turan's theorem. This is called Turan's theorem. This whole thing leads to, it opened up a branch of graph theory, what is called extremal graph theory now. What is now called extremal graph theory. Under certain constraints, what is the highest, largest thing that you can get, what is the smallest thing you can get, etc. These are problems of extremal graph theory. There is yet another proof of Mantel's theorem that I want to hint, but I will not completely give that proof. Okay? I would want you to think about it. And it works like this. So second proof of Mantel's theorem. There are at least half a dozen proofs of Mantel's theorem. And triangle free. So one is define a function from the set of vertices to the closed interval 0, 1. So these take non-negative real numbers as values, satisfying the property that so this is some number. with that given assignment, f is now to be looked at as an assignment. It's a function. I'll give you an idea and you should complete the proof. Here is x, here is y. X and y are adjacent to each other. Let's say x and y are adjacent to each other. Besides y, x would have some other vertices adjacent to it. Besides x, y will also have some more vertices adjacent to it. After all, so I'm just, okay, since I've used x and y, let's use v and w. Okay. So in this sum, you will have f of v multiplied by the sum of all these, f values of all these. And if you call this fr1, fr2, etc., the sum of all these. F of w multiplied by the sum of all these. Assume for that this is bigger, this sum is bigger than that. Okay? Then it would be a good idea, call this weight, f is called weight. F of v is called weight at v. If this sum is bigger than this sum, then to make that sum bigger, it would be a good idea keeping f of v plus f of w the same. Some of the positive thing here could be shifted to v, so that sum will actually increase. It will increase. What is the whole idea? I want to find the maximum. So the problem here is maximize s over all functions. All functions satisfying this constraint. If I know that this sum is bigger than that sum, bigger numbers getting multiplied by bigger numbers is a better idea than bigger numbers being multiplied by smaller numbers. Okay. So what you could do is, you could shift some of this to v. And what that means is, of course you cannot really think about this. I want to maximize s. If I shift all the weight to a single vertex, then s will become 0. That is not okay. That is certainly not okay. I mean, if only one vertex has weight equal to 1 and the other vertices have weight equal to 0, then this s will be equal to 0. That is not okay. But the procedure that I am outlining to you, think about, says that you should just about do that. What it means is you should try to push the weight as much as possible only on two adjacent vertices. And if all the positive weight is on two adjacent vertices, so say v has weight alpha and w has weight beta, the remaining things have weight 0, then I have the situation where alpha plus beta is equal to 1. What is the largest? This is equal to 1/4. This is maximized at 1/4. And that should give answer to this question. Okay, think about this. So that is the idea of this second proof. So S does get maximized when, on the other hand, it is possible to make a weight assignment, each vertex getting weight 1 upon n. Is that clear? I can give weight 1 upon n. I can define f of v equal to 1 upon n for every v. What will be S in that case? In that case, S will be each summand will then be equal to 1 upon n multiplied by 1 upon n, which is 1 upon n square. Therefore, S will then become number of vertices, number of edges in G, Whereas what we are saying is, because this is the maximum. And that shows that E of G is less than or equal to n square over 4. Very different way of proving Mantel's theorem. It completely comes as a bolt from blue. So think about this. Now we, yeah. Okay, tomorrow we meet at 11 a.m. Yeah. Need to look at questions of degree sequences of graphs. So that is one thing I have to look at immediately. Given a graph, the list of degrees of vertices is what is called its degree sequence. The question then would be the other way around. Given a list, when can you construct a graph with that degree sequence? And in particular, a simple graph with that property. So there are two criteria that we look at. One is called the Havel-Hakimi criteria, for which is recursive construction of a graph. The other is a purely intrinsic idea, what is called the Erdos-Galai theorem. So we'll look at these things tomorrow. Thank you.